Students, I welcome you in today's session of physics. And in physics, we will today going to discuss chapter number 10, which is your center of mass. You can see here, this is the chapter we have to discuss today. So in this chapter, what is the syllabus? You first see the syllabus. In this chapter, first we have to discuss about the idea of center of mass. Clear? And in center of mass of two particle system, momentum conservation and center of mass motion, center of mass of a rigid body, center of mass of a uniform rod. Clear? So first you can see here, this is the topic. First one, we will discuss about idea of center of mass. Fine. So every physical system has associated with a certain point whose motion characteristics characterizes the motion of the whole system. Fine. So when the system moves under some external force, then these points move as if the entire mass of the system were concentrated at this point, and also the external force were applied at this point. This point is called the center of mass of the system. I hope you understand it. The motion of the system can be described in terms of motion of its center of mass. Fine. Now we will come to the point number 2. You can see here the center of mass of a two particle system. How can we find out the center of mass of the two particle system? You can see here with the help of this figure. So let us consider a system of two particles of masses m1 and m2. Here you can see in this figure, the first one is m1 and the second one is m2. Clear? Which is located at a point A and B. Let r1 vector and r2 vector be the position vector. I hope you know very well what is the position vector. Clear? Of the particle related to a fixed origin O. Here is the origin, this one. So then the position vector, which is your vector RCM, where CM is the center of mass of the center of mass C of the system, is defined by, you can see here, this is the equation 1, m1 m2 vector of RCM is equals to m1 r1 vector plus m2 r2 vector. Clear? So if how we define it, you can see here, this is the definition. Clearly the product of total mass of the system and the position vector of the center of mass is equal to the sum of the product of the masses of the two particles and their respective position vector. So you finally you can say that, you can see here this one, RCM is equals to m1 r1 vector plus m2 r2 vector divided by m1 m2, this one. Fine. Now there is a derivation given here. Suppose the two particles of masses m1 and m2 are acted upon by an external forces f1 and f2 respectively. Means if the two masses, there is a force over the masses f1 and f2 respectively. So in addition to the external force, they exert upon each other. An internal force also exists between the two masses m1, which is your m1, and m2. Let us suppose the particle of mass m1 is acted upon by an internal force f12 due to the particle of mass m2. Fine. So the force over the mass m1 due to the mass m2 is how much? f12, and the particle of mass m2 is also acted upon by equal and opposite forces, which is your vector f21. Clear? This force is exerted by mass 1 over the mass 2. So due to the particle of mass m1, so we can write here, you can see that the two forces are equal and opposite. So we can write like this, f12 is equals to minus times of f21, or you can write it vectors of f12 plus f21 is equals to 0. Clear? According to the Newton's law of motion, the rate of change of linear momentum of a particle is equal to the net force acting upon it. Clear? So now the net force of the particle is how much? Of mass m1 is f1 plus f12, means the first force and the force exerted by the mass 2 over the mass 1. And also the mass m2 experience the same forces, which is equals to f21 plus f21. Clear? So let v1 and v2 with the instantaneous velocity of mass m1 and m2 respectively, then by the Newton's second law we can write it, derivatives of m1 v1 vector is equals to, this is equals to how much? You can see here, this is equals to d over dt m1 v1 is equals to f1 vector plus f2 vector, and we can also write it like this: d over dt m2 v2 vector is equals to f2 plus f21. Fine. So if we add both these derivatives, what we will get here: d over dt m1 v1 vector plus d over dt m2 v2 vector is equals to f1 vector plus f2 vector plus f12 plus f21. As you know very well, the two forces are equal and opposite, so if we add these forces, the resultant comes out to be 0. So finally we can write it like this form: f1 vector plus f2 vector. So let us write f1 vector plus f2 vector is equals to total external force of the system, which is equals to F external. Clear? Now you can see here the F external force, this one is derivative of m1 v1. Same thing we did here also. And finally, after solving out, I am not going to the deep you can see here you will get the relation like this. So F external force is equals to m1 plus m2 derivatives of the second derivative. This is d2, you can see here is the second derivative, it is written here, this one, rcm by dt square. So d2 rcm dt square is the acceleration of the center of mass of the system. Clear? So this is the equation number 2. You can see here, this is equation number 2. Force is equals to mass into acceleration according to the Newton's second law, F equals to ma. So describe the motion of the total mass, which is your m1 plus m2 of the system, under net external force, how much, acting at the position at a point whose position vector is given by this. This is the position vector. Fine. So you can find out like this. Hence we concluded that the motion of a system can be studied either by applying Newton's second law of motion to the individual particle of the system, or by the motion of the total mass placed at the center of mass of the system by applying external force at the center of mass. Now what's the result of this discussion we had done above? So the center of mass of a system of two particles lies between the two particles and on the line joining them. Clear? Now what's the second one? Is if the mass of the two bodies is equal, or m says that, then what happened? The position vectors expressions changes to like this. You can see here, this is the final expression if the masses are equal. Fine. So thus you can say that the position vector of the center of mass of two particles of equal masses is the average of the position vector of the particles. Clear? I hope you understand it. Now see the third one. If the center of mass of the two particle system lies at the origin, means the position vectors comes out to be 0, then what happened? You can see here m1 r1 vector plus m2 r2 vector is equals to the 0. Fine. So that is the sum of the momentum of the masses of the system about the center is 0. You can see from this relation. Clear? If the position vector is 0, then the masses of the system about the center of mass is 0. Now we will come to the center of mass of a system of n particles. Here we consider the two particles. Now we are going to discuss about the n particles. Fine. So the center of mass of a system of a particle is a point in the system which move in the same way as a single particle of mass equal to the total mass of the system would move when subjected to the same external forces as applied to the system. So let us now consider a system of n particles of masses m1, m2 up to mn with the position vectors r1 vector, r2 vector up to rn vector relative to a fixed position origin O. Clear? So the position vector, this is your RCM of the center of mass of the system with respect to the origin, is defined by this. So RCM is equals to m1 r1 plus m2 r2 vector up to mn rn. Because there are we are taking here you can see the figure up to n particles. Fine. So if we summation all the above terms, we will get the expression like this. This is your expression 1 upon m summation of mi ri vector. Clear? Where you can see this summation of mi is the total mass of the system. Qualitatively, vector rcm represent the geometric point located at the average position of the particle weighted in proportion to their masses. From the above definition, we draw two conclusions. The first one, if all the n particles have the same masses n, then we can write it 1 upon n is equals to summation of Ri vector. That is, the center of mass coincides with the geometric center of the system. Clear? Now see the second one. The origin O is at the center of mass. That is, if the position vector is at the center, then what will happen? This relations MIRI comes out to be 0. I hope you understand it. That is, the sum of the moments of the masses of the system about the center is 0. This is the important one and you should remember it. Now I hope you know very well what is the Cartesian component and polar component. So you can see that we are considering here the Cartesian component of the center of mass. The position vector, which is your RCM and RI, are related to their Cartesian components by this relation. That is, RCM is equals to XCM plus YCM j cap and ZCM k cap. We are considering in the 3 dimension like this. X, this is your X, this is your Y, and this is your Z. Clear? So these are the 3 axes and we are considering their Cartesian coordinates. So finally you will get here the center in this is in terms of center of mass, and if you write it in the x-axis direction, the 3 components comes out to be xi I cap plus yi j cap plus zi k cap. I hope you understand it. Making this substitutions in equation 1, you can see here this is the first equation. Then what we will get here, xcm, which is your center of mass, is equals to mixi. Similarly, ym equals to yi, and the same thing 1 upon m miezi. Clear? Now we will going to discuss center of mass of a rigid body. So a body is said to be, I already told you that what is rigid body. A body is said to be rigid if it does not undergo any change in the shape by the action of force. Means if you are applying the force over the body, it does not show any change in itself, then we can say that that is a rigid body. Clear? However, large, more appropriately, of a rigid body is one whose constituent particles retain their relative position even when its motion is under the influence of a force. So a rigid body having continuous composition is a system of closely packed particles. Clear? The number of particles in a body is so large and their spacing is so small that we can treat the body as so it is a continuous distribution of masses. So to obtain the expression for the center of mass of a continuous body, we can divide the body into infinitesimal small element. You can see here, this is the small elements xi, y center of mass, y center of mass, and z center of mass. Then we can write this relation like this. But as you know very well that this is dm, integration of dm means the mass of the whole body. So we can write it like this. In place of xcm, what we can write it? You can see here in place of xcm we can write it 1 by n integration of xtm. Same thing we can do for the ycm and zcm, which is your center of mass against y-axis and z-axis. So if we combine all the terms, we get or we can write in the 3 scalar expression like this. RCM is equals to 1 by m integration of r dm. I hope it is clear. So for a rigid body of regular geometrical shape and having uniform distribution of masses, the center of mass, you can see here it is written that is their geometric center. This is the center of mass of a triangle and this is the center of mass of a cone. You can see here. For example, the center of mass of a uniform sphere, that is hollow or solid, is at its geometric center. This is the geometric center you can see here in figure A is at C. And same thing if we talk about for a thin rod of uniform cross section and density, the center of mass is at its geometric center. So the center of mass of a circular ring is at the center of the ring where there is actually no matter. The center of mass of a thin triangular plate is at the point of intersection. You can see here this is the point of intersection of the 3 medians. So there is the center of mass at intersection of 3 medians. Clear? And for a right circular solid cone, the center of mass is at the point on its axis at a distance h by 4 from its base. This is the important one you should keep in mind, that where is the center of mass of a cone is situated. So it is situated at the height of h by 4. You can see here from this figure, where h is the height of the cone. Clear? Now we talk about center of gravity. So every particle of matter in a body is attracted by the earth and the magnitude of this attraction force is directly proportional to its mass. The single force that we call the weight of the body is the resultant of all these forces of attraction. Clear? The direction of the force on each particle is towards the center of the earth, but the distance to the earth center is so great that for an all particle purpose the force acting at different particles of the body can be considered parallel to each other. Therefore, the weight of the body is the resultant of large number of parallel forces acting at different particles of a rigid body, and the point through which resultant is supposed to is known as center of gravity. So this is the definition of center of gravity. I hope you know it very well. Now we come to center of mass of a uniform rod. This concept is very important, so understand it properly. What is going on here? Look, you can see that. Okay, students, this topic we will discuss in our next lecture. Clear? Till that, do study. Thank you, class. Thank you.